Okay, so ask you to draw the graph of a voltage function. Corresponds to closing a switch, opening a switch on a constant voltage source, right? Now, the way I would draw that graph is I would draw a t-axis, and I would draw something like this, without labeling it, because I didn't give you a frequency or a voltage. And that's not it. Okay? Make sense? And you don't know when time is zero. So that's all you got. You went and put a y-axis in there and started at t equals 0 with a voltage. It's not the initial condition I had in mind. I don't know about you. Okay?
You said we start with it open, right?
Yeah, you can start with it open, and then the capacitor could have a charge on it. The stuff would be going on, right? Okay? The inductor could have a current in it. The capacitor could have a charge on it. So anything could be happening at t equals 0, right?
If we did have an inductor, it wouldn't look like this anymore, would it?
The voltage function. Well, the voltage from the source would. The source voltage function would look like this, and then everything else would have to follow from that. So what we're trying to do is build up the ability to analyze this, because you can't do it using the techniques that you have in differential equations today. First order, second order, higher order isn't going to help you. Okay? Now if you got a sine function driving it, then it's fairly easy to analyze. We've done that. Okay? And if you have, well, if you have a function you can write in closed form based on your fundamental functions, exponentials and polynomials and rational functions and trig functions, okay? You can at least speculate on how to do it, okay?
Are there other functions that...
Well, you take composites of all those things and inverse functions and stuff. You got, yeah, there are other functions. I mentioned, I think, Bessel functions. Just comes right out of differential equations. I was talking about that the other day. Legendre polynomials, which you get out of linear algebra. Okay? There are all kinds of functions. You have a differential equation with some parameters in it, then the solution can be a function of those parameters. Okay? And you get eigenvalues and stuff, so you get whole infinite sets of functions that hopefully span the space of the solutions of that equation. And hopefully even they're mutually orthogonal, which makes them really easy to deal with. But you don't really know what that means yet. You got an idea, you recognize some of the words and some of the concepts, which is a good start. Okay? So are there other functions? Yeah. Okay? I mean, there's a Heaviside function. Whoever suspected that? Okay, well, actually another fundamental function you get in pre-calculus is step functions. Okay? I usually don't even do those till the end of the course because you got to know they're there. Okay? If you get absolute value functions, they're also step functions, and they can be important. This is kind of like a step function, but not exactly. Okay? You could do it that way using mod and stuff like that. Okay, anyhow, there's your voltage function, okay? And the most convenient way to model it is with the Heaviside function, because you can do differential equations with anything you can Laplace transform. As you know from what we did maybe about a month ago, okay? You can transform a differential equation using Laplace transforms, and the whole premise and all the details are pretty simple. You can derive it just using integration by parts, okay? And we might have to revisit that, but that will come back to you, okay? So what we have now is a function like this driving a circuit, or an impulse function. We apply a force to a mechanical system, an oscillating mechanical system, maybe with drag, okay? With some kind of a linear restoring force, even a non-linear restoring force. You know, there's a force, then there's no force. Then there's a force, there's no force. Always the same force, okay? So that's the kind of function we want to be able to model, so we've got to be able to use the Heaviside function to build this thing. So my first question for you, and I think we might have done this, but can you show me, in terms of Heaviside functions, can you give me a function that's 0 up to here, 1 here, and 0 from here on? And let's just say, just for starters, so we put a y-axis on here, like you went and did for this one, which is okay. Just asking what it would look like. You gave me more detail than necessary, so it wasn't as general as it could have been, but that's not going to be a problem. Okay, so right there is the function that I want to define in terms of Heaviside functions.